Now, let's move forward to the theoretical aspects and start by philosophy from ancient Greece. Now, philosophy originates from the Greek word philosophia, which is a compound word composed by the word philo, friendly, and word sophia, or wisdom. Ergo, philosophy means, loosely speaking, being friends with wisdom. Now, currently and officially, modern philosophy is the study of general and fundamental questions such as abstraction, existence, reason, knowledge, values, mind, and language. And you can see that philosophy is an interchangeable field where it relates most of our fields together. And such questions are often posed as problems to be studied or resolved. Now, we can look at theory of knowledge and global perspective, but still inside of this type of studies, we can always find philosophy, because philosophy just means friends with wisdom. If you like wisdom, you are a philosopher. Now, mathematics or mathematica originates from the Greek word mathema, which means learning. Now, we have the axioms such as a dot and a simple line. And these are considered axioms because they are self-proven. We cannot prove them. We know that they are there, at least in an abstract way, and we can use them in order to describe reality. We cannot really pinpoint a point in the universe because we have to discuss about its size, and usually we call this as 0 dimensions. Although it can have different dimensions depending on your pen. If your pen is big, you're going to have a big dot. If your pen is thin, you're going to have a thin dot. But what is the actual size of the dot is a matter of speaking. Now, a line also is the same thing. We cannot really be sure if we connect dots on the same way, we can create a straight line. But if we see that microscopically still, we cannot be sure that it's exactly straight. Therefore, these notions, we know that they are idealistic and we can use them to describe reality, but maybe they are far a bit from reality. However, they are useful and we use them in order to describe several descriptions. For example, you can go straight ahead to this path, you say to the fellow human. Now we have also numbers, from natural numbers to rational numbers to real numbers to complex numbers. Of course, we have algebra to discuss and understand what are the relations between the numbers, the letters, and the operation between all these aspects of mathematics. We have geometry, which is evident by discussing the shapes and understanding the shapes that we see around us. Then we have sets, such as sets of mathematical objects, such as the sets of two geometrical spheres or two sets of numbers, and so on. We have functions that relate a set of numbers to another set of numbers, and we have the derivatives, which tell us how much a function changes in a corresponding variable. We also have limits, where we show the limiting behavior of functions in some extreme cases. And this also is related to the notion of derivative. Now we have the antiderivative or the inverse process of a derivative, which we call integrals. And basically, these tell us what is the area under the curve of the function inside the integral f of s. Now we have also probabilities that they talk about the chances of an event happening. We have the statistics, which tell us about some statistical aspect of those events. And we have theorems, such as the three-dimensional Pythagorean theorem, and all that with mathematical proofs, and not only. Now, physics. Physics, physiki, originates from the Greek word physi, and it means the study of nature, basically. Here in this image, I try to put most of the physics that we're currently understand. And here on the top left corner, you can see a high accelerating car, which is most probably Ferrari. And this acceleration and motion can be described by the Newton's second law of motion. The force is equal to the mass times the acceleration, or in more advanced calculus terms, is basically the change of the momentum p as a function of time t. It's proportional to the mass of the object times the second derivative, or how the function of the trajectory of the car changes as a function of time. Now, we have these balloons. If you don't wrap them, they are neutral. If you wrap them, they create the same type of charge. They become negatively charged because we have removed the positive charge. Therefore, they start repelling each other. And this can be described by the electric force, which tells us that the force of one balloon to the other is some constant k times the charge of one balloon times the other charge of the other balloon, inverse proportional the square of the distance between the two balloons, 1 and 2. Now, the very small scales, if we go further into the fundamentals of matter, we can see a quantum form. And quantum mechanics and special relativity describe this quantum form. And these theories tell us the basic fact that energy is a manifestation of matter, E is equal mc squared, up to some factor. This is what happens at the small world. Now, the very large world, we have that the energy is a manifestation of the curvature of space-time. And here you can see how a trampoline, which is flat, as you can see, is affected locally by a massive object. When this object touches the fabric of the trampoline, it makes it bend. In the same way, any massive object, any object with energy, affects the space-time around it. And that's why some people, when they talk, you see their energy that they radiate basically can change the space-time around them. So gravity or general relativity states that geometry is a manifestation of energy, and the other way around, the energy is a manifestation of geometry. And G, nu, which is a component of geometry, is more or less E nu, which is the component of energy in the universe or any physical system. And this is a description of the very large world. Of course, we don't have a coherent and well-accepted theory that describes both the large world and small world. However, we have several efforts and a lot of our understanding have been put in order to match this type of theories in the small world and large world. However, we still have well-accepted ideas that we use in order to describe the small and the large world with mathematical aspects, and we call this study cosmology, which is the study of the smallest to the largest objects. Now, cosmology can be done using the Sloan Digital Sky Survey. Basically, this is a telescope that took images of galaxies from the very far distant universe. And as you can see here, people have took these images, they put them in a simulation, and then they made the simulation where an observer can travel in this sea of galaxies. And you see here how the galaxies are structured together due to the gravitational effects. They are tied together. Some places we have a lot of galaxies, some other places we don't have a lot of galaxies. In some places, the galaxies are packed, creating a node. In some places, you have thin filaments or some sheets. And we have also some voids, absence of galaxies. Now, to describe and explain the position, timing, and motion and properties of the whole universe, we use experimental and theoretical physics, which results to the study of cosmology. But where did it all came from? The universe. However, we do not know the whole universe, and we are here to explore and advance our understanding further. Let's see what is the current picture. This is the current picture. Without words, we have the Milky Way, where we are located, and we see this image with our telescopes. But what's here, we don't know, and currently people are trying to understand theoretically and experimentally. Now, we have the Big Bang here. What is that? Quantum fluctuations. We have energy that fluctuates in a quantum level, and this creates several things. It creates inflation, 10 times minus 32 seconds after the Big Bang. It creates the BPN epoch that I encourage you to try to see what is exactly. We have the recombination and decoupling time that I'm going to explain later. And 380,000 years after the Big Bang, we have the CMB, the cosmic microwave background radiation. And this is emitted light that we can observe with current radio telescopes, microwave telescopes. Now we have also the dark ages. Here, our telescopes cannot observe a lot of things, and we have some window in the universe that we don't have a lot of information. After that, there is the reionization epoch. This is 400 times 10 to the power of 6 years. And in that case, you see that the matter starts being ionized again, and we have a signal to our telescopes. After that, we have all the elements that interact together. It creates the first planets, and then solar system, galaxies, and collision of galaxies, and we have the galaxy phase transition. And after that, we have the acceleration of the universe. And all this happens at an expansion, which happens 13.8 times 10 to the 9 years, or 13.8 billion years. Now, the Baryon Acoustic Oscillation is a phenomenon that happens in the early universe and happens all the way through up to the late universe. And we can see and observe its phenomenon throughout. Therefore, we can categorize this effect in different times. We have 300,000 years after the Big Bang, the hot Baryon Acoustic Oscillation, BAO, 360,000 years after the Big Bang, the recombination, 380,000 years after the Big Bang decoupling, 7 times 10 to the power of 8 years after BB called BAO, and about 13,000 billion years after the Big Bang, today not 13,000, 13 billion years. Now, either in the late universe with density fluctuations of the galaxy distribution, or in the early universe with temperature fluctuation of the total matter distribution. This can be observed. And this is a very, very rough description. Let's start with the first category. 300,000 years after the Big Bang, the universe was hot and dense. There were two main forces, an outward force and an inward force. The outward force was basically the interaction between the baryon, lepton, and photons. This produced high temperature, high kinetic energy, and outward pressure to the particles. However, on the opposite side, we have an attractive gravitational potential of matter, and this creates the inward gravitational force. Counteracting of these forces create acoustic oscillations to the structure. For example, here you see a combination of baryon, lepton, and gamma that they interact with each other, and they are in a specific location, but this happens everywhere in the universe. And each bubble here interacts with each other. There is some gravitational force, and there is some kinetic energy force around them, pressure. Now, 360,000 years after the Big Bang, we have recombination. The universe cools down at the point where the baryons are combined with the leptons, and acoustic oscillation freeze at the very large scales. Here you see we have baryon and lepton, and the gamma are left alone. And the same happens for any other bubble in the universe. All gammas are gone outside, and they are not interacting anymore with baryon and lepton. We have the first atom. And now, since this happened, we don't have this soup of particles. However, these particles are freeze, and we have the gamma. And 300,000 years after the Big Bang, we have the decoupling. The photons cannot interact anymore with atoms, and they free stream as a cosmic microwave background. And we are left with the frozen baryon acoustic oscillations that they start evolve with time. So here you see how the free streaming of CMB happens. All the gamma are going away, and the other particles, they are stay there, and they are kind of frozen, but the time passes, and the universe is expanding, and therefore this pattern stays there. Now, 7 times 10 to the power of 8 years after the Big Bang, we have the cold BAO, and the first galaxies appear along with quasars. For example, this image tells us that when we had this particular configuration and the interaction was happening everywhere, after some time, this interaction starts to split, and one on the left, it becomes a galaxy, on the right can become a quasar. And this is more or less how the first galaxies and quasars appear in time. Now, today, after the Big Bang in the universe, we can observe these phenomena, and we can observe them with telescopes that tell us about the early universe, 380,000 years after the Big Bang, or the late universe by just looking the optical wavelength of elements in the sky. And by studying the temperature fluctuation of the cosmic microwave background and the density fluctuations of galaxies in the late universe, we find a particular pattern. This pattern is 150 megaparsec, or 10 to the power 25 meters, and we can find it in the early universe or at the late universe. And let's see, what is this particular scale? We can have in the early universe the hot BAO and the late universe the frozen BAO. Let's see this pattern in more detail. Imagine that we have an energy fluctuation somewhere. You see this peak of energy. And this, with time, expands and creates this particular pattern of energy. This size is 150 megaparsec. But this doesn't happen in one spot, it happens everywhere. And now we have a combination of this effect from everywhere. And this is the energy and the space-time interaction. However, in this space-time and energy interaction, we have galaxies. Therefore, we are going to populate this particular pattern with galaxies. And this is a simulation that we built, and we can compare the simulation to the image from telescopes in the sky. And here, for example, if you do that, the size, if we have a zoom, you see regular galaxies. So we have put in our simulation the galaxies that we see. And let's make measurements. Take two galaxies, a pair of galaxies, measure the distance. This distance appears 1. This distance also appears 1. This distance appears 1. Now this distance appears 1 as well, close by to the other. This is another one, this is another one. But you see, after some time, you have a repetition of these distances. And how many of these distances there are which are repeated is given by the frequency and separation graph. And this creates the Baryon Acoustic Oscillation peak, the BAO peak. This is a characteristic signal of this type of structure that you have seen before. Now, the relativistic universe. We have seen simple description of reality. However, our current universe can be described by a light cone. And let's see how that works. We have the action principle that tells us that changes in the action are 0. And this, with the right ingredients, we will have the nice equations of motion that describe the whole universe. Now, this is space, this is time, this is future, present, past. And here you can have a light cone, and here is the last scattering surface. Here is your world line, where you are traveling in time. Now, in this past light cone, we have the cosmic microwave background. And here in between, we have the galaxies and supernova, and these emit light, and we can observe it in our world line. And we also have some black holes or gravitational waves in between the CMB and our world line. And you see, as time passes, even though we don't move, still we obtain some particular information. So as time passes, we always obtain new information. Now, before the cosmic microwave background, how we can be sure that the temperature fluctuation in this past is the same as the temperature fluctuation in this past? And since they are not causally connected, we discover inflation. And we say that before the last scattering surface, there were still more time left. And these 2 points, they had their own light cones, which are connected with each other from the quantum form that we've seen before. Therefore, in order to describe reality, we have the light cone and the right equations of motion and the right ingredients, such as dark energy and dark matter, that fill the space. We have inflation, which is imprinted in the large-scale structure, and we have some primordial feature signals that can be observed from the early universe or from the late universe. Now, what's another way to describe the theoretical Fermi? This is a set of per two Boltzmann-Einstein equations that have the following ingredients. You can find reference there in this thesis. And basically, we have the metric, which is how the geometry of the universe is described, and this is connected to all the matter ingredients out there. We have neutrino and photons on the left that they create together the radiation. We have lepton and baryons that together they interact with each other with Coulomb scattering and they create the baryons. The leptons and photons are interacting with each other with Thomson scattering. The baryon and dark matter, they make together the total matter of the universe. And since the lepton is small amount, we consider them as baryons as well. And therefore, the full matter is basically dark matter and baryons. We have also the dark energy component, and all of these components, they are all interacting with the metric and the curvature of space-time. Now, if we make measurements, we find that only 5% is baryons. It's the matter that we see. A fraction of that is radiation. 26% is dark matter, and 69% is dark